So I hope I've convinced you that what really holds proteins together are intermolecular forces, IMFs. But not all IMFs are created equal, and some contribute to stability in protein structure, and some contribute to specificity. So when we think about the stability, that's really the energetic, enthalpic compensation. So structure formation is unfavorable from an entropic standpoint because entropy is unfavorable when we're creating more order. And so when we're having molecules and atoms move less, that means it's an unfavorable entropy. So being able to compensate that with entropy is key. So we'll talk about in a second what is the biggest contributor to protein stability. Specificity, just to sort of define what we're thinking about, specificity we really want to define as the intermolecular forces that dictate who is next to who. So the IMFs that dictate who is next to who. And then again, stability, this is the IMFs that are really enthalpy that holds proteins together. Sorry, it's really small up on top there. Okay, so let's take a second here and refresh ourselves with the intermolecular forces that we have. And highlighting, when we think about the bonds that we have in biological molecules, when we think about covalent bonds, these are really intramolecular. So kind of within molecules, so between atoms. And so we're going to talk about covalent bonds in a minute, but when we think about these non-covalent intermolecular forces, London dispersion forces are the weak. Then we've got dipole-dipole interactions, hydrogen bonding, and then electrostatic or ionic interactions. So let's take these kind of in turn, and let's think first about our London dispersion forces that we have here. So despite London dispersion forces being the weakest intermolecular force, we've talked about them also being the most prevalent, and truly these are the most important contributor to protein stability. And here's how and why. When we think about what really dictates and drives the stability within protein structure, it is the hydrophobic effect. So the hydrophobic effect remember, is the tendency of nonpolar substances to minimize their contact with water. So we're going to have nonpolar substances minimize their contact with water. And at the end of the day, what this means is that we are putting nonpolar amino acids on the inside of proteins. So nonpolar amino acids are on the inside of proteins. We call this hydrophobic collapse. And do you remember when we talked about the structure of proteins and what really happens when we form tertiary structure? It's the interaction of side chains in proteins, and lots of intermolecular forces sort of drive that. But if those side chains are interacting and contributing to the stability of protein, it's going to be because they're nonpolar residues that want to find the interior of our protein and get away from water. So we call this hydrophobic collapse, and it's really the hydrophobic effect driving the stability of holding this protein in this globular shape. Okay, so let's move up our hierarchy here. And let's talk next about hydrogen bonding. So hydrogen bonding is something that can also contribute to stability, and here's how. When we consider these structures, so these structures are our alpha helices and our beta strands that interact to form beta sheets, those are secondary structural elements. So this is secondary structure. Let me zoom in here so that we can just kind of get a better look at what we have here, remembering that secondary structure is held together by hydrogen bonding between backbone atoms. Okay, so these are going to be backbone atoms There's another video out there that will go through more of the details about the structural specifics of these secondary structural elements. But we have hydrogen bonding between the carbonyl oxygen and the hydrogen on the nitrogen of backbone atoms, and that contributes to the stability of secondary structural elements such as alpha helices and then our beta strands that interact to form beta sheets. So stability in tertiary structure is largely driven by the hydrophobic effect in those nonpolar residues. In secondary structural elements is hydrogen bonding to hold those elements or those secondary structural elements together. When we think about the specificity piece, again, that's dictating who is kind of talking to who's next to who. There's two main forces that we're going to talk about with that. And let's talk first over here about our ionic interactions. I don't know how well that yellow is showing up there, but we've got ionic interactions here. Okay, and so when we see these in proteins, these are what we call salt bridges. Okay, because we've got positively charged amino acids, basic amino acids. Here we see lysine and arginine interacting with negatively charged amino acids. Those are generally our acidic amino acids like glutamic acid and aspartic acid, forming an ionic interaction there. Okay, the last piece to kind of highlight, and this is not really an intermolecular force, and even though covalent bonds are what drive and hold together primary structure in amino acids, that's the sequence of amino acids. Those peptide bonds are what hold those amino acids together. We can have covalent bonds that dictate who is talking to who. And in particular, this specificity, I should put yellow around this too because those salt bridges contribute to specificity. But a large contributor to specificity, and we're going to see this with the protein insulin when we do our insulin case study, is thinking about things like disulfide bonds. Okay, so peptide bonds are an important contribute to specificity. That's a covalent bond that we have there. And then disulfide bridges are an important piece that are going to, here we can see, oops, not there, we can see these disulfide bridges, cysteine residues in insulin. And those peptide bonds, or those, disulfide bonds are really important for kind of getting the correct pieces next to one another in a small protein like insulin. And so we are going to spend some time talking about this in our insulin case study. Okay, so mapping on those intermolecular forces as we see them contribute to protein structure, some of them are important to contributing to the stability of protein structure, the hydrophobic effect in London dispersion forces, and then hydrogen bonding in secondary structural elements will contribute to the stability of a folded protein structure. But things like ionic interactions and covalent bonds like disulfide bridges, those are what really contribute less to overall stability and more to the specificity of who is going to be next to one another in an overall protein structure.